Hi guys, this is Tesla Coil build log part 8, and for no particular reason I'm recording the first part of this narrative from These things that call themselves Toslink jacks arrived today. It's not real clear if they're actually transmitters or receivers or both. From the footprint it looks more like a receiver, but from the price being $3 something Australian, it lends me to believe it's an LED. The RS page isn't real clear either, and neither is the data sheet that it links you to. It talks about a series of 7 odd models. I think the key when you get down to the correct looking one is the fact that there's 2 different model numbers, and it seems to indicate that there's a separate transmitter and receiver, where the white on black LCD modules arrived today. They're still the same old HD 44780 controller. It's probably a bit more modern to have these fancy colours that are plain black and white, but it's not black enough, as you can see from the circuit board. So I've got the same epoxy enamel, painted it with no surface preparation, just masking. I had an interesting result where the enamel pulled away from the wires, as you'll see in the photos coming up. I have an abundance of silence and privacy and peace. The electronics guts on the table so far should be approaching a black and white theme. First time powering up. I'm recording the audio for this after the fact, so I know what happens. I think in the end I used 2 lower value current limiting resistor for the backlight compared to the other display. So if you look to the right, you can see smoke coming out of the display. You'll also notice the display was working for a while, but it stops working right there. Zooming in for the smoke there, that's about $20 down the tube. LEDs in the backlight still look and work fine, and so does the transistor driver that was powering it. So yeah, that's quite strange, but on to the next one. Take 2. I've added 390 ohm resistance in series with the current limiting for the backlight. Yeah, it is working there. The problem with this LCD module in general is that you need a voltage below ground on the contrast so you can see it head on, and it looks nothing like the advertisement. The backlight is also never uniform. That's not just the photo, there's always dark spots. And here I've used a potentiometer on the contrast just to make sure it's not something to do with the PWM circuit, and I get the same result. There's just nowhere above ground to find a place where I can view it head on. So yeah, I'm done with it. And surprise, surprise, use a 10-year-old one, you get the full range of contrast and everything works fine. Interesting that, isn't it? This one has a trap of its own. Some bright spark decided to take an industry standard interface and reverse the polarity so that pin 1 is actually the positive supply, but I fell for that one years ago. So underneath 2 layers of sheath, the optic fibre cable is really just a bit of acrylic. So I've dug up a data sheet for the transmitter module. It is an LED with a driver chip, so it wants a power supply of its own and 0.1 UF decoupling capacitor. So I won't pretend to know what the chip is for, other than maybe to provide a constant brightness over some varying voltage range. Going back a little bit in this series, I wrecked my first Toslink cable by cutting it in half so I could use an LED just shining into the open end, so I don't have a Toslink cable with 2 proper ends on it. But the system so far does work just by shoving the bare end into the jack, and then I get some reliability if there's not too much ambient light. It appears they do rely on a bit of mechanical precision to hold the cable up against the LED and the receiver. This LCD does look a lot better than the previous ones in this video series, but maybe this one isn't so great for the camera, and I might have to dull the backlight down to make it more visible for future recording on video. There's a YouTube video that goes into the applications using cores as suppressors or filters for high frequency noise. The microcontroller guts in this project might have its own power supply, but it's not completely isolated from the Tesla coil. There's an I/O pin connected to the solid state relay, and I don't know if the solid state relay makes a good isolation for any AC that is superimposed on the DC signal. So I'm not going to go into any attempt to block kilohertz frequency noise in this video, but just a random test from a ferrite in my junk box. I have a signal generator generating something around a 37 megahertz signal, and that's where I found that this particular 6 windings around this particular ferrite caused an attenuation greater than 50%. I see it clap out. Having grouped the 4 identical cores together with tape, I've passed 25 turns roughly through the whole tube as a group, and that seems to be effective down to 3.3 to 3.9 megahertz. If you consider effective to be attenuating the input signal by about 50% or more. The clunk switch I'm using now just short circuits the inductor to switch it in and out of the circuit. The signal generator producing this signal is outside of the shot, but you can see the waveform increase in amplitude as I move away from the effective frequency. Here I've added about 30 more turns to the coil assembly, whatever you want to call that thing. It's the black wire is the extra turns. So now I've got a total of about 55. Because I'm adjusting the frequency at the signal generator end, the displayed frequency on the oscilloscope is only valid when I'm pushing the button, and hopefully it comes through so it can be read on this video. And that was about as much wire as I can fit through these cores. Now it's an effective suppressor at about 1600 kilohertz, which is getting there. I know there are more effective filters once we're getting down to these low frequencies below a megahertz. It just might be a bit of overkill for a problem that's really preemptive that I haven't had yet. The microcontroller software for this project is the sort of thing I could keep playing with for a while, but I'm at the stage where I'd call the electronics part finished. Except for one last thing, a momentary latching power switch for the keypad. I'll probably omit the details from my videos. There's an EEV blog video that's right on the subject that's pretty good. Dave's pretty clear in this video. He wants his to be independent of the microcontroller, but I'll probably use it. Typically you'll use the button to turn the microcontroller on momentarily, and from there it'll hold a transistor on to keep it powered. Given that a device is centered around a microcontroller, I strongly prefer that, because then the software has the ability to turn the hardware power off, like in a calculator if you didn't touch a button for 5 minutes. I can't believe how dusty this thing's gotten just sitting around since I started it. Well, I've heard back from the company that's laser cutting the supporting part for the primary, so the next video should definitely be mechanical, and I should have the Tesla transformer part assembled. So that'll be good. I'll see you next time.